So what I'm going to do today is just do some examples because we didn't do any example last time. So these are examples based on what we discussed last time. That is, we are testing hypothesis based on difference of means, two means of two populations. So you have an hypothesis about the difference of uh, means of two population as to are they equal or one is bigger or the other is bigger, and you're trying to test that. So let's first look at this first example, and this is from the book. This is let me put it down. This is problem 10.8. So what you have is some organization conducts some kind of a survey, and based on survey questions, they give some points as to the attitude of managers towards minority employees. And the higher the number is, that means the more is there some kind of higher score means that they have negative attitude, more negative attitudes towards the minority employees. So they take, and what they did is just chose a certain number of managers and gave out these samples, and then they analyzed the data based on their gender. So you had a certain number of males. Actually, in the data, there were 151 male managers, and female managers were 108, because it was just a random collection, didn't have to be equal. And what they found, that if they computed the average numbers for males, it was, on that survey, it came out to be 85.8. And then they also computed the standard deviation of the sample of males, and that was this number. Similarly, they computed the average for the female managers, and it came out slightly less with this standard deviation. Now, this data is suggesting that the attitude of female managers is more positive towards the minority employees compared to male. And they want to see that what this indication which they see from these two numbers, that the male managers have a higher average in this sample, does this have, how much statistical significance does it have? Based on this sample, can they conclude that females managers have a better attitude towards the minorities? So to do that, they will have to put a hypothesis, and they want to prove this, because this seems like being indicated from the data, that the average score on this survey, and higher the score means worse attitude, average score of males minus females is greater than 0. So essentially, all it's saying is the average score of males is higher than the females. So on average, females have lower score based on this test, based on this survey. So they will start with this hypothesis, the reverse of it, the opposite of it, that the average of the males in the population. Now we are not talking about this sample now. This sample is an evidence for this statement or for this statement. Based on this sample, what we can say for the general population, for all male managers and all female managers. Assuming, again, this assumption is always there, that the general population has a normal distribution on these numbers. So they start with this null hypothesis, which they want to reject in order to prove this. Now, in doing this, we have no assumption or knowledge about the population standard deviation, or population mean is obviously not known. That's what we are trying to find out from here, a statement about that. But the population standard deviations are also not known, which is a fairly common thing to happen in practice. And also, we are not assuming that they are equal for males and females, nothing like that. All that information you have about the populations is through this sampling. So no assumptions about population distribution, except that they are normally distributed. So in particular, we are not assuming, do not know standard deviations for males or females. Female, I should say, managers. And secondly, do not assume that the standard deviations for females and males are equal. We're not assuming that. So in that case, what you have is, we are going to use this result. The result is always same. The result is that the sample average, if you have two populations and you take samples from those two populations. No, so there's a question by Zara. The only way standard deviations would be equal is if the data was the same. No, I'm not talking about the standard deviation of the sample. I'm talking about the standard deviation of the population. Those could be same for certain reasons. For example, it could be like you're testing a medicine which lowers, for example, let's say the temperature. And for some reason, you can assume that someone on the temperature, on the medicine or not on the medicine, they will have a same range of the of what kind of temperatures you can measure. It's only the average which is reduced because of the medicine. So if you will be testing something over there, you have two populations, one on medicine, one not on medicine. The means are expected to be different, but the standard deviation could, for some reason, be assumed to be same. But in this case, we are not assuming anything like that. Now, this is the main result, which we will be all the time using when we are testing the difference of means of two populations. And we had used this before as well, that this difference, because this is normally distributed, mean of average of one sample. So statistical mean, expectation value of the average of one sample is a normal variable. Similarly, the the average of one sample, like in this case, the male managers is a normal variable. Similarly, the average of the other population, second population, in this case, this is the women managers, that's also a normal variable. Then you can show that the difference of the two is also a normal variable. So we can consider this variable, and this is going to be a normal variable. And out of this normal variable, you can obviously construct the standard normal. What you have to do is you have to subtract, let me use another color, the population means, because those are equal to the expectation values of these sample random variables. So this is equal to population mean of the two divided by the standard deviation of this difference variable. This we have a formula for. So the variable we are looking at is this. We will have directly this formula if we knew the standard deviation of the population. But since we don't know the standard deviations of the population, then we know that what we do is we have to introduce the t variable. And t variable is almost like the normal variable, standard normal, except that you will be using let's write m first. You will be using this standard deviation, which is an average, a weighted average of the two. So this will be computing for you the required t variable. This difference will be following this t variable distribution because we didn't know the sample at the population standard deviation. And whenever you use the sample standard deviation, you have to, you have to replace your standard normal with the t. And this minus in this case would be 0, because what we have here is we're testing this hypothesis that the difference is 0 or less. And the alternate is when it's much bigger than the 0. So our t, which is almost like a normal, is like this. It's symmetric. And it's distributed for us at 0. Because this is the boundary of our null hypothesis. And if we find a number here, somewhere here, then we reject this hypothesis. So the average, this average is assumed to be 0, and we test against that. So it is this t variable which we have to look at. But over here, you have an index for the t variable. How would we find this index? So remember, whenever we were if we are analyzing the sample averages in general, I'm not even talking about this, if you have a sample average, it's a normal variable with this standard deviation. and you have an average. Well, I should put in the population average. This is the normal variable you look at. But if you don't know this, if sigma is not known, then you look at the sample and compute S, sample standard deviation. And instead of Z, you use the T variable. And this is S over under root 10, which I can also write as S square over N. Now, in this case, since we have two columns, two separate samples, one for the men, one for the women, it turns out that you have to take to compute the proper standard deviation, which you have to divide by, like here, is something like this, but it's a weighted average of these. It's just this number, but including both of them, one data and the other data. So that's the whole point of it. And over here, this new was n minus 1, where n is sample size. But now, new will have to be computed. It's based on this some kind of an averaging, and there's a formula you can use. It always works. So compute the degrees of freedom for the t variable using this formula. It's just a big mess, but it doesn't matter. It's just a small computation. Minus 1. Now, when I do this, do it for this problem. If I do this, I'll need this number upstairs and downstairs. So let's just compute it, and I'll also need it in here. So it's handy if I just compute it. This turns out to be 2.424, while this turns out to be 1.378. Now, over here, let me see. Wait, someone wants me to scroll up. Is this good enough, or should I go further up? Is this okay? Okay. So I have these two numbers, and I just have to put these in. So I find that the new is whole square over 2.424 square over 150 plus 1.378 square over 108. So this gives me, let me just do this computation quickly. Upstairs, I get 14.45. Downstairs, I get 0.0392 plus 107.0177. So this whole number becomes 253.7. Now what you need to do, this new is supposed to be an integer, but in using this formula, you will never get an integer. So you just round it off to the closest integer. So new would be 254. Now I want to test the hypothesis. To test the hypothesis, you will reject